Hello, this is Skewers by James Sinclair. The first puzzle in his Artisanal Sudoku Volume 115, I think. Yeah, it is a puzzle involving thermos and killers, and also this one square over here. Alright, so let's take a look at the rules. Normal Sudokus apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. We have killer cages, so the sum of digits in the cage is equal to the small number in the top left corner. That means that those digits, for example, would have to sum to 15, those digits have to sum to 7, and so on for every other cage here. We have thermometers, so digits on thermometers must increase from the bulb. So we have like thermometers that branch out here. They have to increase from the bulb, so whatever this is, you know, your sequence would have to increase like this, basically. And yeah, it can increase in any way it likes as long as every digit is greater than 1 before it. And lastly, the digit in the cell of the shaded square must be even, so that's an even digit. It's either 2, 4, 6 or 8. And that's it. Yeah, so those are all the rules. With that, let's just begin solving. Alright, so first we're going to look at the cages that are more constrained. So for example, the 15 cage over here. Actually, we can actually put the digits in there really quickly because there are only 2 ways to make 15. It's either with 7, 8 or 6, 9. However, we know that it cannot be 6, 9 because 9 cannot appear in the center of a thermal at all. In fact, if a 9 exists on a thermal, it must be at the very tip. And that is because if 9 was anywhere else, that would imply that there is some digit greater than 9, which there isn't. So this must be the 7, 8 pair, which is placeable. And that digit must be greater than 8, which therefore can only be a 9. Cool. Okay. Now, what else am I seeing? Maybe this, yeah. This 8 has a few options. It's either 1, 7, 2, 6 or 3, 5. However, it can't be 1, 7 because 7 is already in the row. It cannot actually be 2, 6 either. Because if it was 2, 6, that implies that that digit is greater than 6. However, all digits greater than 6, which are 7, 8 and 9, are all already in the row. So that would have no option. And therefore this cannot be 2, 6. It must be the last option, 3, 5. And therefore has to be in increasing order like that. That digit must be greater than 5 as a result, but can't be 7, 8 or 9. So that digit only has 6 as an option. So that's cool. Now that digit has to be less than 3, which means it's either 1 or 2. Ooh, hold on. Yes, okay. Those digits sum to 8, which is very interesting. Now, we already know that 8 has 3 options, either 1, 7, 2, 6 or 3, 5. However, none of these 8 cages can have 1 in them, because similar to the 9, if 1 is on a thermal, it must be at the bulb. That's because if 1 is anywhere else, it implies that there is a digit smaller than 1, which there isn't. So those digits cannot contain a 1 in them, and therefore will not be the 1, 7 pair. They therefore have to be the 2, 6 and 3, 5 pair. And because 2 exists somewhere in this pair, that digit cannot be a 2, it must be a 1. And also 2 cannot be on the outside. Whoa. Because that would imply there is no digit between 1 and 2. That would imply there is a digit between 1 and 2, which there isn't. So 2 cannot be on the outside, it must therefore be on the inside. And wherever 2 is on the inside, must be paired with a 6 to make an 8. So 6 must be on the outside as a result. We can do the same for 3 and 5 actually. 3 cannot be on the outside, because if it was, that would imply that between them must exist a 2. But that will form a sum of 5 and not 8, which is bad. So 3 can't be on the outside, it has to be on the inside. And wherever 3 is, must be paired with a 5, so 5 has to be on the outside. I hope that was decently explained. Yeah. Alright, those digits form a pair. They have to be 2 and 4. And to make 7, 2 either pairs with a 5 or 4 pairs with a 3. But 2 can't pair with 5 because that would imply that would break the thermometer sequence. It must increase upwards. So it must be 3 with 4. And so 2 goes there. 3 resolves this pair. 2 must be with 6. Up here we can put a 3 and a 5. And there we go. Alright, that digit is less than 3, so it's either 1 or 2. But the 2 in the box means that it must just be 1. Alright, fair enough. Okay, those digits could tell us something maybe. Yeah, because 12 has only 3 options. It's either 39, 48, or 57. It can't be 39 because 9 is already in the box. It can't be 48 because 4 is already in the box. It must therefore be 57 and therefore must be in increasing order like so. That digit is greater than 7 but cannot be 8, therefore has to be a 9. Which gets us a lot of the way there. This is a triple consisting of 3, 4, and 5, I think. 3, however, can't be in those, so 3 goes here, leaving a 4, 5 pair. This is also a pair. I think they have to be 6 and 8. And as a result, we have 3 triples over here. That has to be 1, 7, 9, I think, to finish the row. And here to finish the box, we have, I think, 2, 4, 8, if I see correctly, yeah. We can remove 1 from that cell though, because there are no digits greater than 1 over here. And similarly, we can remove 2 from that cell because you cannot have so many digits less than 2. This could be a 4 though if it goes 1, 2, 3. However, that breaks the 10 cage. So I don't think this can be a 4. If it was a 4, yeah, then those digits have to be 1, 2, and 3. This digit is therefore going to sum to 5, which doesn't work. So this can't be 4. It has to be 8. Which, since this is greater than 8, must just be a 9. There you go. In fact, this summing to 10 probably gives us something. Yeah, 10 has a few options, but it can't be 1, 9, 2, 8, or 4, 6. It must therefore be 3, 7, which must be in increasing order upwards. This digit is therefore either 1 or 2 again, because it's less than a 3. Can I solve this one? I think so, yes, because 12 again has only 3 options, but it can't be 3, 9, or 5, 7. It must therefore be 4, 8, which is in increasing order. So that digit now is greater than 8, it must be a 9. 4 is also 2, 4 pair. And finally, I think there's a triple over here. What is this? 4, 7, 8, I think. But this can't be great. It must be greater than 6, but it can't be 7, so it must just be an 8. This can't be 4. It can't be an 8, so it must be a 7, meaning 4 is down here to finish the box. And we could probably figure out that cell, I think. I mean, it's even, but it can't be 4 or 8, so it has to be 2 or 6. I don't know. Okay, what else do we have? This 11? Not really. I think 11 still has a couple options. Yeah. Okay, what else do we have? Any missing things I'm not seeing over here? Probably like this 8 or something like that. Oh, I guess... I mean... this entire column being thermometer is kind of suspicious to me. I could ask a question like, where does 2 go? And it could either go behind the 1 or up here. But I don't think it can go anywhere else. And then similarly, oh, where does 9 go in this column is the right question to ask. Because if 9 is on a thermal, which it will always be, it must be at the end of the thermal. So it must be in one of those cells. 9 here removes 9 from that cell, so 9 must be up there. Cool. So now we can actually figure out this 11 cage. Because 11 cage now cannot be 2, 9, 3, 8, or 4, 7. It must therefore be 5 and 6, which again must be in increasing order. This allows us to place a 2 in that cell. And of course 2 in this row, in this column, sorry, now can't be behind the 1. It can't be there either because those digits are always going to be greater than 4 and 6 respectively, so 2 must be here. Therefore last digits here are 7 and 8, which 8 here resolves. Now probably we're going to look at the last thermal over here to finish things off. Like those digits have to sum to 8, right? But we see that it cannot be 2, 6 or 1, 7, so it must be a 3, 5 then, and it must be in increasing order. So there it is. That digit is greater than 5, but can't be 7, 8, or 9. Wow, so that is just a 6. Awesome. What else do we have? I mean, I think at this point it's just regular Sudoku, right? Yeah, at this point it's just regular Sudoku. So let's try and figure out some stuff. None of the pairs written here are resolvable yet, I think. So we still have a ways to go. We can place a 3 in this box though, box 1. 3 must be here. What else do we have? I want to generally look for duplicate numbers. So 5s here are duplicated, and those cells can't be 5. 5 here can't be there. Actually, we can do more about that. Yeah, in fact, let's start with a 5 in this box. The 5s here and here tell us that 5 must be there, which is useful because now 5s here, remove 5 from those cells, so 5 must be there. Which gives us a triple here consisting of 1, 2, and 4. Now that can't be 2 because of the 2 in the row, but still not resolvable. What else do we have? Again, looking for repeated digits. Maybe here somewhere there's something good. Like? No, I was gonna say like something, but we don't have enough digits to tell us. Could probably place, we could probably place a 7 in this box. 7 must be here in this box. Which gives us some 7s, but not all of them. Yeah, in fact this leaves a pretty large gap as to where the rest of the 7s are. I think 7s are here in this box, here in this box, and here in this box. So no. Alright, there is a triple here consisting of 1, 8, and 9. This digit can't be a 9, that digit can't be an 8, and that's it. Alright, fine. The last digit in this box we haven't seen yet besides 1, 2, and 9 will be a 6, which must be one of those cells, I guess. So in this box, where does 6 go? 6 here would always see those cells. This 6 up here sees that cell, so 6 has to be here, which gives us a triple here. There it is. This is 1, 3, and 5 as a result. And 3 can't be here. Actually, we can do better. 5 can't be in those cells, so 5 goes up there. This 3 would resolve this 1, 3 pair. 5 here resolves this 4, 5 pair, and that gives us more to work with. This is 1 or 2. Those digits are therefore 4, 8, and 9. Yeah. What can we do? 9 can't be there. 8 can't be below it. But this could be anything. Okay, so that really didn't give us much, but we work with it. This is also a triple consisting of 1, 2, and 3, I believe. Yep, and 2 and 3 here means this can't be a 2 or 3, it's a 1, which gives us a 2 here and therefore a 3 there. 1 would be meaning an 8 goes here. 1 also can't be there, so 1 must be here in this row. 9 is over there, which does a lot of stuff. Yeah, firstly 8 resolves the 6, 8 pair. Secondly, 1 resolves this 1, 7 pair. And hopefully that does something for us. We're gonna have to work with these pairs first. Like this has to be 6, 9, nice. And those have to be 2 and 4, I think, which is resolvable. Okay. This is 6 and 7, which I can't figure out yet. And then we have 1 and 4, which I also can't figure out. Okay, very useful. This forms a triple consisting of 6, 9, and 8. This can't be 8, so in fact in this column 8 must go up here. Now that can't be 8, which means 8 in this triple has to be over here, which hopefully does something for us. Don't know what it does. It does, I see a 1, 2, 4 triple over here though. Not sure if that's entirely useful, but that at least tells us that those have to be a 6, 7 pair, which could help. Not really. I mean, this forms a 1, 4, 9 triple, which is definitely useful because of the 1, 4 here. So this can't be 1 or 4, it must be 9, which gives us a 4 there, a 1 there. 4 means that's a 9 over here, and 9 resolves this 6, 9 pair. 9, which puts us a 6 up here, which gives us a 7 here. That resolves this 6, 7 pair. This can no longer be 1. This digit to finish the column, is a 2, which resolves this 2, 4 over here. That resolves this 1, 4 pair, which in turn resolves this 2, 1 pair. Solving the puzzle in 13 minutes and 8 seconds. Cool, very smooth. I like this one. Alright, so yeah, that was Skewers by James Sinclair. Hope you enjoyed this video. I'll see you guys next time. Bye bye. Hello, this is Ticket Stop by James Sinclair, part of his Artisanal Sudoku Volume 115. It is a quad German whisper puzzle. I haven't seen these constraints. No, actually no, I saw quads like last week. But yeah, alright. No German whispers in a while, so I'm happy to be back working with them. Let's take a look at the rules. Normal Sudoku rules apply. So place the digits 1 to 9 in every row, every column, and every 3x3 box. German Whisper. So along the green line, digits must differ from their neighbors by at least 5. So whatever this digit is, let's not choose a number like that. So whatever this digit is, the digits beside it, or digits along the line next to it, have to be at least 5 away. So those digits are valid. And yes, so this is a valid pattern for your German Whisper. It has to go all the way on a loop. So for every single digit, its neighbors must be at least 5 away. Next, we have quadruple circles. A digit inside a white circle must appear in at least one of the 4 cells surrounding that circle. So let's take a look at this quad maybe. It has a 3, 5, and 9 in it. So in the 4 cells highlighted here, there must be at least a 3, at least a 5, and at least a 9. You can in fact have duplicates that look like this. This is okay. So yeah, those are all the rules. With that, let's just begin solving. I'm actually very impressed that there are so few clues here and this actually makes something work. I mean, to be fair, a lot of miracle Sudokus do look like this as well. So that's great. Let's do some talking about, like, refreshing on how German Whispers work, right? There is one digit that cannot appear on a German Whisper line, and that digit is actually a 5. Because if you think about it, the digit 5 does not have any digits of, does not have any digits that are at least 5 away. You either need 0 or 10. So can I do that? Oh, I can't put a 0 in here. Can I put a 1? Oh, it gives you a 0, 1. But yeah, you get it. 5 cannot have any digits around it that are at least 5 away, and so 5 cannot actually be on the German line. We can already put that to use in placing a 5 in this quad. The 5 can't be on the German line, and therefore 5 must be here. Okay, another thing that is also rather interesting is that along a German Whisper line, polarity has to alternate. And that is polarity meaning whether digits high or low. And so if you picture a number line, for any 2 digits that differ by 5, one has to be below 5 and one has to be above 5, right? So like, let's say your number line, looks like this from 1 to 9. You can't choose 2 digits from below 5 that are differing by at least 5, and the same for the high digits. So it must be 1 from here and 1 from here. And therefore, for any digit over here, let's say it was a low digit, which I'll put with blue, the digits beside it must be high, which I'll put with orange. And yeah, we can actually already probably do stuff with the 3, 4, 5 over here. Because 3 and 4 must appear on the line, but both of them are low digits. They cannot therefore be beside each other, and therefore they must be apart like this. And so those digits are the low digits 3 and 4. And actually, because we have these low digits, we can go ahead and continue placing low digits on every other cell, because we know they must alternate. So once we have that, we can place high digits in the remaining cells, and we have this sort of nice little pattern over here. And so, right, that digit I think is a 9. Firstly, we can place 1, 2, and 4 outside because all of them are low and therefore cannot be here. But we know 4 is in one of those cells, and 4 only has one partner, which has to be 9. Which means that wherever 4 is, would have this as a partner, and therefore this must be 9. So that's another digit. Yeah, 4 only has 9 as a partner. Similarly, 6 only has 1 as a partner. So those are also 2 numbers or 2 digits that are important to us. 5, 4, and 6 are all very special in their own way. Okay, how will we do this? We know that's a low digit, I guess. Does that really help us? I don't know if it does. I mean, it could be 3, it could be 4, it could be something else entirely. It could be 1 or 2. Oh, it's this one, isn't it? Yeah, this one. Actually, that's really interesting. This 1, 2, and 3 here imply 1, 2, and 3 are not on the line. Therefore, if this is a low digit, what must it be? It must be a 4. And we already know 4 has only 4 only has one neighbor, which is 9. Actually, yeah, that does put a 3 here because it resolves the 3, 4 pair. I was going to say that this can't be 4 because that places a 9 here, but it's a lot simpler. Just that 4 can't be there. Alright, now those 4s, remove 4 from those cells, placing a 4 up here. And actually, yeah, 3 only has 2 neighbors. It can only be next to 8 or 9. That digit cannot be 9 anymore, so it must be an 8. That digit is a 1 or a 2 because it can't be 3 or 4. Because 4 is not 5 away from 8. Cool. What else have we got? This? Oh yeah, this is the exact same idea. 7, 8, and 9 are all high. So what high digit could this be? It has to be a 6. Which has to be next to 1s. That's the only thing 6 can be next to. The 1 resolves this 1-2 pair. Which does something maybe. Actually, this 4 means that digit must be a 9. I didn't see that. So that's cool. And yeah, that's valid because they differ by at least 5, which means that it could differ by more than 5. What else do we have? All of these, yeah, the low digits are actually annoyingly not seeing each other. So this one actually doesn't see any other low digit right now, which is really funny. It manages to dodge all the low digits at once. That's kind of cool. Okay, let's color those in as being low digits. Yeah, when we talk about polarity, or in fact, polarity and parity, which means odd or even, the interesting property is that from the digits 1 to 9, there are always 4 lows and 4 highs, as well as 1 5. So yes. Okay, what else can we do over here? 5 here? Well, 5 can't be there because it's on the line. 5 can't be here because 5 is already in the box. So 5 is in one of those cells. Is that useful to us? I wouldn't say so. No. Although, yeah, okay, sorry, I can actually do stuff over here because this forms a triple. It cannot be 1, 6, 2, 7, 8, or 9. So those digits just have to be 3, 4, and 5. I think same here. Those digits have to be 5, 6, and 7 to finish the box. I can probably do stuff with that. Like 4 can't be in those cells, so 4 has to be up here. And in fact, that's a low digit, so let's place that down. The 5, 6, 7 is a little bit worse because we can't resolve that. We're all working with... Yeah, we're focusing a bit more on lower digits right now. Okay. 4 here means that digit can't be a 4. But it could be a 1, 2, or 3. So that doesn't really help. 9 is one of those cells. Oh, actually here, yeah, we can place 4 and 6. Well, not really, but... Oh yeah, we can, 4. 4 over here come in those cells, so 4 in this quad has to be up here. 6 come in those cells, so 6 in this quad must be here. That digit is a low digit, so 8 does not go there, 8 goes down here. And that digit is some low digit, which isn't 4. Okay, so there you go, we can color more stuff in. Actually, that digit now can't be 6, 8, or 9, so it must be a 7. 7 does have 3 options, I think. No, 7 has only 2 options. Right, 7 is only next to 1 or 2, so those digits are 1 or 2. Which now means that those 3 digits must be where 3, 5, and 9 are located. Because this cannot be 3, 5, or 9. Therefore what? 9 can't be there. 5 can't be there. And that's all we have. Okay. Anything special that we haven't seen yet? I don't think so. Nine over here must be one of those cells. I think. I mean, yeah, it's not really that helpful. 8 can't be there, so 8 must be one of those cells. Which now means in this box has to be one of those cells. Which does not help. So that's useful. Well, I do know that in this row, where does 9 have to go? It can't be in those cells. Therefore, has to be here. I guess more logically, where does 9 go in this box? It has to go there. So that's our last high digit in this. Whoa! I drew a line. Whoops. Has to be as the last high digit. Sorry, in this row. So those digits are all either low digits or 5. And since this digit can't be a 5, it must be a low digit. So let's place that in there. Just for record keeping measures. And in fact, none of those digits can be 5 either. So those are all low, which means 5 in this row has to be here. So now that digit can't be a 5, it's a 3. which means 9 goes up there, 5 goes over there. Awesome. I don't want to keep coloring. I mean, I feel like I should, but color the high digit. Alright, so now 3 can't be there, so 3 in this row has to be in one of those cells. Actually, in fact, that forms a 1, 2, 3 triple, so I should mark that first. 3 can't be here, 2 can't be there, and this could be anything, I believe. So that forms a 1, 2 pair over here. Therefore, 4 in this box has to be down there. This has to be 6, 8 pair, which now means that those digits cannot be 6, and 6 must go down here. That gives us more digits to work with. That's a high digit, those are high digits. That is a low digit. Cool. Now what can we do? 9 here resolves this 9 over there, so 9 has to be up here. I guess this forms a 2, 7, 8 triple, which I'll mark down. Oh, there wasn't any real use marking them down before, but I guess now it's slightly more convenient. So that digit cannot be a 9. Or a 6 in fact, so it must be 7 or 8. That digit also can't be 9, so that is a 6, 7 or 8. I mean, it could be a 6 because this could be a 1. I mean, because it is a 1, so this could be a 6. If this is like a 1 or something. Which it very well could be. This could be any digit from 1 to 2. Oh yeah, it can't be a 3, can it? Because if it was a 3 only has 2 options, 8 and 9. But none of those digits can be 9. Meaning if this was a 3, those would have to be both 8, which doesn't work. So this can't be a 3. It's only a 1 or a 2. Okay. That's a triple. You can see that. This has to be 6, 7, 8, I think. 6, 7, 8. That digit can't be 7 and something something, but those digits are all high digits. So that's great. 6, 8 pair. Cool. Right, 5 in this box. 5 in this box must be over here. Okay, cool. Cool. Oh, this 5 resolves this 3, 5 pair. Why don't I see that? I wonder why. What do we have here now? I don't know. Okay, this one's a triple. They have to be, what? 2, 6, 8? But that doesn't really help us. Doesn't give us any colors either, because... yeah, just because. This requires a 5 somewhere, which we can place. 5's here. Imply that 5 must be in that cell. And so we need 1, 2, 3, and 7 in this box. 3's are useful. Remove 3 from those cells, so 3 goes here. That forms a 1, 2, 7 triple, which, you know, 3 in the corner. Yay! 3 in the corner. Alright. This 8 actually removes 8 from that cell. Didn't see that, so 8 goes here. This has to be 1, 2, or 3, but in fact, can't be a 3, so it's a 1 or a 2. So 7 in this row has to be up here. Nice. Does that help us? Gives us stuff. Like, that's a 1, 2 pair up there, which does help us, right? Right, because 2 can't be in those cells now. So that's a 7, 8 pair, which means 2 goes here, and also this has to be a 6 as a result, which must be next to 1. Awesome. Wait, we're doing a lot of work here. Sorry, I'm stuttering a lot. The 1 resolves this 1, 2 pair, which gives us a last digit here, which I think is a 4. Yeah, those digits have to be 2 and 9, and therefore this forms a triple consisting of 3, 7, 8. Now 3 can't be in that cell, so 3 must go here. And I think at this point we no longer really need to worry about the colors, so I'm gonna get rid of them. No more colors. This is a bit harder to read, honestly, so I'll just keep them until the end, because I can see slightly better with the colors on for some reason. This could be any digit from 1 to 2, yeah. This is also 1 or 2. That's fine. Okay. Sorry. This has to be what? 3, 7, 8 as well. 3 can't be there. 8 can't be there. Something's happens here. What are we missing here? A 2? Yeah, but 2 is one of those cells and we can't figure out which one. Oh, this 2 resolves that. Why didn't I see that? That's a 1. So 2 goes here, 1 goes here. This must be a 3. That must be a 2. That must be a 1. This 2 actually tells us that 2 can't go there, so 2 goes here. And therefore something. Two in this box. I mean, it's a bit easier to say 2 in this row because of the 2s here come in those cells, so 2 must be here in this row. The other way I saw it was that this and this form an X-wing, which means none of those cells can be 2 either. And that's because in these 2 rows, there is 1 2 here and 1 2 here, which is 2 2s. And in 2 rows, there are only supposed to be 2 2s. So nowhere else in this row can there be another 2. Right. Don't know if that's really useful, but that gives us another triple over here, which have to be 5, 7, and 8. Does that help? 8 coming in that cell. Oh, so nice. 8 has to be up here. That resolves to 7, 8 pair. So that now can't be an 8. It's a 3, 7 pair. 7, no. Actually, that forms a triple, sorry. This is what, 3, 5, 6? And that cannot be 5. This cannot be 3, which does something apparently. Don't know what it does. Oh, in this column, it's another triple. Yeah, we can actually work with that. This has to be 5, 6, and 7. And actually 5 can't be in those cells because of the 5s here. So 5 goes up there. Cool. 8 means that can't be an 8. So chocolate teapot. Very nice. 6, 7 pair resolves this 5, 7 pair. And now those digits have to be 4 and 9. Which I cannot resolve somehow. Wow, really? Yeah, alright, cool. Sorry, blanking out again. What digit have we not seen here? 3? Yeah, I've not seen a 3 here, but it's one of those cells which I don't think we can figure out right now. Oh, sorry, this 6. I didn't see that. It resolves this 7, 8, 7, 6 pair, which resolves this 7, 8 pair. And that gives us stuff. This now can't be 6 or 8, so it's a 2. And this 8 means that can't be 8, so that must be 6, meaning 8 goes up here. That gives us another chocolate teapot. Amazing. This 2 resolves this 2, 9 pair, which resolves this 4, 9 pair, which gives us a 1 over here. Gives us a 3, 8 pair over here, which also cannot resolve. I think it's all down to like the final stuff. Anyway, the last 2 digits in there would be 4 and 7, which we can resolve, I believe. Yep, this 4 does that. So 7 goes here, 4 goes there. That resolves this 3, 7 pair, which in turn gives us the rest of these 3 rows. 6 goes here, 7 goes here. Oh, another 3 in the corner. We got both of them now. Awesome. 3 resolves this 3, 8 pair. And finally 8 resolves this 6, 8 pair. Yep, solving the puzzle in 18 minutes and 11 seconds. Well, I think this is a bit slower than before actually. Like in terms of my solving. There you go. Nice. Yeah, I think the line was very fun to work along. I haven't actually seen an idea like this, so that's very cool. Okay, well I hope you enjoyed this video. I'll see you guys next time. Bye bye. Hello, this is Kodiak by James Sinclair. At least I believe that's how you pronounce the word. It is the third Sudoku in Artisanal Sudoku volume 115 and is one of the harder ones. In fact, this one is rated as a 9 out of 10 difficulty, I think. Yeah. Alright, so let's take a look at the rules. Sorry. Normal Sudoku is applied. So place the digits 1 to 9 every row, every column, and every 3x3 box. Killer cages. So the sum of digits inside each cage, so for those over here, is equal to the small number in the top left corner. Therefore, those digits will sum to 5, and those digits will sum to 4. Next, we have arrows. So the sum of digits along an arrow, let's say this arrow over here, the sum of digits along an arrow is equal to the digit in the connected circle. So those digits will sum to that digit. If this was an 8, you could have 1, 2, 5. This is valid. And digits may repeat on an arrow if allowed by other rules. So you could have something like this. This is okay as well. Next we have Renban lines, which are these purple pinkish lines over here. They contain a non-repeating set of consecutive digits in any order. So what that means is that this line over here contains 6 consecutive digits. So let's say 2, 3, 4, 5, 6, 7. That's 6 consecutive digits in any order. So maybe, you know, this is valid, sorry, because it contains 2 to 7 in some order. And yeah, that is holding true for every other Renban line. And finally, digits in cells separated by a black dot have a 1 to 2 ratio. So those digits, for example, those digits are the only black dot there is. Digits in cells separated by black dot have a 1 to 2 ratio. So one is double the other. So this is valid, that is valid, something like this is also valid. And I assume not all dots are given, so it's possible for any other pair to have a 1 to 2 ratio as well. Alright, with that, let's just begin solving. This might take a while because this is, I think, one of the hardest puzzles of his I've ever done. So let's see how it goes, shall we? The 4 is the easy one first. There's only one way to make 4 in 2 cells. It is 1, 3. You could also use 2, 2, but that would repeat digits, which is not allowed. The 5 has 4 options. It's either 1, 2, 3, or 4. Alright, so that is the easiest one we can do. The next easy step we can do is this 3 long arrow. Because those 3 digits must all be different. They are in the same row and in the same box, in fact. And therefore, they have to be at the very least 1, 2, and 3. Meaning that digit is at least a 6. But I think we can do even better. Because we have those 5 digits over here. And in fact, we have those digits over there as well. So the minimum of those digits are actually 1, 2, 3, 4, and 5. Because they're all in the same box. So they must be different. Which means that those 5 digits will add up to at least 15 if they are at least 1, 2, 3, 4, and 5. And those 2 cells would therefore add up to at least 15. Now, can there be a 6 in any of those cells then? The answer is no. Because if there was a 6, the other digit would have to be a 9. Because, you know, those have to sum to at least 15. And so, whichever way it works, you could have 6, 9 here or the other way around. The issue with that is because both digits are on the same Renban line, they must be 3 consecutive digits. However, 6 and 9 are not part of 3 consecutive digits. You have 2 digits between them, 7 and 8. And therefore, you cannot put any digit in here that would form a consecutive set of 3. Which is to say that 6 cannot appear anywhere in here. Additionally, that digit is also at least a 7. And that is because, again, we know 6 cannot be here. And that digit can't be a 5 because for this to sum to at least 15, this would have to be at least a 10. So it can't be anywhere below 6. So it's 7, 8, or 9 as well. We can probably work on that digit now, which I believe is at the very least a 6, if these are 7 and 8. Then this would have to be at least 6. So this is at least 6, but it could be 6 because 7 and 8 do add up to 15, which you can fit in here. So yeah, this is at least a 6. It could also be 9 if this was 7 and 8. So yeah. 9 can also appear outside, and if it did, this could sum up to like 17, which is, you know, that is 2 degrees of freedom. So yeah, 15, 16, 17 are possible options here. Yeah, and I think a hidden a hidden deduction you could have on Renban lines is that digits may never repeat on them. I think it's actually in the rules. It's non-repeating set, so it's not really a deduction, but yeah, those cannot both be 9s, meaning that at most those will have to sum to 17. Which really means that you have to have a certain number of digits in here. For example, if you didn't have a 1, then 2, 3, 4, 5, and 6 at the very least would add up to 23, I think, which is way more than what we can have. So there must be a 1 in here. There must also be a 2 in here, and then also a 3 in here. You could have no 4 in here because 1, 2, 3, 5, and 6 add up to 17, which is the most we can have. So yeah, but we do know 1, 2, and 3 must appear in those cells. And this 1, 3 pair does remove 1 and 3 from that cell, which helps maybe, but not quite. I think that might lead to us looking at this over here. Sorry. This row is quite interesting because of that. A dot has a few options, and I think I've said this many times before, but the possible pairs you could have on the dot are 1, 2, 2, 4, 3, 6, and 4, 8. 4, 8. So that's the only digit you can have on the dot. Now, what we cannot have on this dot is a 3, 6. And that's because 3 is already in the row. And same for 1 actually. Which means that 1, 2, and 3, 6 are all not options we can have. Which that means that this has to be either 2, 4, or 4, 8. So there must be a 4 here. It's either 2, 4, or 4, 8. So yeah. Another thing we can say is that, can this have a 6 on it? Yeah, 1, 2, 3, 5, 6 we say is valid. Another thing we can say about the dot is that that dot cannot have the digits 5, 7, and 9 on them. So 5, 7, and 9 have to be elsewhere. Which means that they're in here. I mean 5 could be there, but 7 and 9 have to be outside, because 7 and 9 cannot be here either. Okay. Wonder what else we have to do then. This maybe? I was thinking that those digits, I don't know how close they would be, but because this is in any order, right? Those could just be 1 apart. You could have this be like a 7 and then this be an 8. And that's technically valid if everything else still follows the rules. So I don't think we have that figured out yet. I mean, interestingly, right. Well, no, I'm not right in saying that. I'm like, this set of digits, can they have 2 on it? And the answer is yes. Because even though 2 would need a 3 on the same line, that 3 could be elsewhere on the line. Even though it does not appear here, it could be somewhere up there. So yeah, there could be a 2 in here. That's valid. Is that digit at least a 5? No, because that digit could have a 1. That digit could be a 1 or a 3. We haven't proven that 1 and 3 must lie here yet. Even though if we did prove that, I think that would be pretty helpful. Wow. There really isn't much to do here. Oh, I see. If we still look at these arrows, it is really cool though, the geometry of this. Those 2 cells, oh, those are different. But I can say that those 2 cells is, this digit has to be here and this digit has to be here, is my my conjecture, and I think I want to prove that. So let's start by, we know those are different cells, right? And we know that therefore they can't both be 7. So one of them has to be greater than 7. However, we know that this can at most have a 7 in it. It cannot have anything greater. And the reason why is because if you take the 4 other digits and have them be as low as possible, 1, 2, 3, and 4, you would only have 7 left before you hit the maximum of 17. Which means your last digit can only be as large as 7 and no larger. So 8 and 9 actually cannot be on the arrows at all. But we know those digits are not the same, and therefore even if one of them was a 7, the other digit would not be a 7 and would be a greater value. Now whatever that is, whatever that value is, would have to be not on the line, not on the arrows, not on its Rambam line, and you know, whichever it is, right, we can assume by diagonal symmetry here that we can assume either one to be the greater. and say that, well, assuming this is a greater, those are not that digit then, and that digit therefore has to be here. So I'll change this color to pink. And now, this digit is therefore going to be whatever digit that is, assuming it's the greater one. Back to the smaller one. Firstly, if it was a 7, can you still put a 7 on the line? And the answer is no, because if it was a 7, to even put a 7 on the line implies that your sum has to be 17. But if the 7 was already on the arrow, then the other digit would have to be 10 to make 17, which doesn't work. So in fact, if 7 was here, that 7 could not be on the line, could not be in here, could not be whatever it saw, and would have to be there. And if it was greater than 7, then the same idea applies to whatever digit we put in here, which must again cannot lie on this arrow, cannot lie on its line, cannot see those cells, and therefore must be here. So this digit is always there, and this digit is always there, which means those digits are also 7, 8, and 9. Ooh, okay. So there you go. That's really weird. But I think that's where we also do this. Okay. Okay, great. I think we have made decent progress here. Now, they could still be 7 though, because the 7 no longer appears on the line. But... those are all 6, 7, 8, or 9. Can I find one last digit that is 6, 7, 8, or 9? I don't think so, honestly. Like, that digit could be it could be a 5, because it can't be a 4. It can't be any less than that because 1, 2, and 3 are already in the box. So it doesn't have to be 6 and above. It could be 5, right? Because if it was, you could have this be 1, 2, 3, 4, and 6, and that's okay. Pretty sure it could also be 1, 2, 3, 4, 7, and I think that would be okay as well. So yeah, this could be a 5. So this is at least a 5, at least. We know that it's at least a 5. I mean, I suppose that 5 cage up there could be helpful in determining what that cell could be. But not ultimately, no. I don't see it doing anything else. Okay. Maybe we look in here. Yes, because of those blue cells. I think it must be there. It can't be here, right? Oh no, it could be. It could be 7 with 2 1s. But it can't be 7 with 2 1s. Oh, that's so cool. Alright, so let's figure out where the cyan goes in this box. That cyan or blue has to be one of those cells. However, can it be on the arrow? Let's assume it is. If it is, then those digits would have to be at least 1s each to make 9, which seems possible at first. So you could have like 1, 1, 7 here with the sum being 9, but that's actually not plausible because the 1s, whoever it is, would see all of those cells. Wow. So even if this 1 was below here and 7 was above, they would again see all of those cells, which eliminates 1 from the arrow, which we know cannot happen. Wow, so even if it was 7, it cannot be on the arrow. And if it were 8 or 9, it couldn't be on the arrow either, because that would force this digit to be at least a 10, which doesn't work. And so, none of those arrows could be 7, 8, or 9, and therefore the cyan, or the blue, whichever you want, has to be in that cell, which is again a 7, 8, or 9. Oh, wow, that's so cool. Okay, can we do something similar with that? I mean, maybe. Where does pink go in this box? Again, we know it. Yeah, well, it can't go there. And the reason for that is actually a lot more simple. If this was 7, 8, or 9, then this digit, there are 2 distinct digits, sorry, because they're in the same box. So it have to be at least 1 and 2. But 1 and 2 with 7 means this has to be at least 10, which doesn't work. So we already know that pink can't be here. So pink is one of those cells. Can it be here? And this 4 might be useful, but I think it can if this was an 8. That could be a 7 or a 9 to pair with the 8, and then this could be 4. So unfortunately, I do think that this could theoretically be pink, could be whatever digit that is, if this was an 8. If this was a 4 or a 2, then obviously not, because 2 and 4 are not close enough to 7, 8, or 9 to make a triple. In fact, 4 with 7 still requires 5 and 6 between them, which we can't fit into one digit. But yeah, it could technically be pink. Right, so actually hold on, yeah, let's think about what do those digits have to be at least? Do they have to be all different? I think the answer is yes. Either that or 4 repeats. Because if there were repeated digits, right, wherever they were, there will have to be one of them here and one of them in this pair. And whatever they were would have to see all those cells if it was repeated. And because those cells all contain 1, 2, and 3, we therefore know the repeated digit cannot be 1, 2, or 3. Because having the repeated digit there would remove 1, 2, or 3 from this arrow completely. And so to have your repeated digit, at the very least that repeated digit must be a 4. If that last digit was a 1, your digit sum would have to be at least a 9. So with a repeated digit, that will have to be at least 9. Without a repeated digit, this will have to be at least 6 because 1, 2, and 3 will give you at least 6. So I'm pretty sure this is at least a 6. Yeah. Which... well, the interesting thing is that cell sees all of these. Well, yeah, it does see all of this. Could this therefore not be a 6? No, if it was a 6, this could be 7, 8, and 9. That's valid. I don't know. I don't see anything to do after this. Although, no, 9 could be made of 2, 3, and 4. That's also valid. I was like, does 1 have to be on this arrow somewhere? And the answer is no. Because 9 again could be made of 2, 3, and 4. If it was repeated 4, 4, you would need a 1, but no. 9 could be 2, 3, 4. And obviously you could have high digits on there. You could have a 6 with a 1 and a 2 to make 9. That's also valid. Okay, I think I should remove the pink coloring here because, yeah. What can I do here now? No, I think I should keep the pink coloring just to make sure I don't accidentally try and put whatever this digit is into here. Alright, let's think about... oh yeah, let's think about blue. Blue in this box cannot be here because similarly to pink, this would form a sum of at least 10. So cyan has to be somewhere in here. I keep interchanging them, but I think this is cyan. I don't know. Which means in this box, that digit has to be in here somewhere. Is that good for me? Is that useful? I don't know. I don't really understand, no. I feel like there is something here. Could this be 1, 2, 3? Can I fit in 1, 2, and 3? Like, let's just try to fit in some digits here. You could have a 1 here, therefore 1 there. This could be 2 and 3. So 2 and 3 will be outside. So like, let's say like this. And this could be... yeah, no, this is fine. So it is possible to fulfill it if you had 1, 2, and 3. Okay. Just trying to test out a theory here. But yeah, that is possible. Which means I cannot eliminate anything. I don't think the Renban line is going to be useful in doing that either. Alright, fine. If this digit was in here, this must be an 8, so therefore this wouldn't have to be it wouldn't be able to become an 8. So if this digit was here, it wouldn't be 8, basically, what I'm saying. Is that useful? I don't think it is right now. No, not really. Okay. One, 3. So that could easily be 1 or 3. I don't know. 6 requires 7 and 8, which means 9 goes in there. But I think that's fine as well. Maybe? I feel like I have to do more arrow shenanigans. Like something like, you know, those two digits, or those two pairs would have to sum to at least 10, because 1, 2, 3, and 4 sum to at least 10. Therefore, those digits have to sum to at least 10. But that's very easy to accomplish, considering how far apart they could be. They could be anywhere from 1 to 2, 4, 6, 1 to 5 apart. So yeah, it doesn't really help us with anything. Oh, hold on. Pink cannot be here, right? Yeah, because we know, similarly to blue, blue can't be on the arrow, so pink, by that same logic, can't be on the arrow as well. So pink must be in here somewhere, which tells us something. Because of the pink here and wherever the pink is here, none of those digits are pink. Is that useful? It might be in saying that, well, if pink was 7, then those digits would just have to be 1 to 6. Which is the lowest it can be, but still plausible. And you could have 4 and 6 on the outsides that sum to 10. Then if pink was a 9, then we have a lot more options. Although I suppose that, okay, wait, what digits have to be on the 6 length Renban? Have I ever figured that out? If you look at a number line from 1 to 9, can I actually write that in? 1, 2, 3, 4, 5, 6. Oh my god, you can, but it's so incredibly tiny, it doesn't make any sense to do that. If you have the digits 1 to 9 in a number line and you chose 6 in a row at random, or not at random, but if you chose 6 in a row, you will always have the digits 4, 5, and 6 on it. And a way to think about it is, if you chose the one on the smallest side, you would have 1, 2, 3, 4, 5, 6. And if you choose one from the highest side, you would also have 4, 5, 6, 7, 8, 9. Which means that the digits 4, 5, and 6 are all going to be, you know, in that sequence no matter which set of 6 you choose. Which basically means that 4, 5, and 6 have to appear on the line. Ooh, wait, hold on, that's good. Because the most important digit there is a 6, which must be on the line. And therefore that digit can never be a 6, because wherever 6 is on the line would see that digit. So that's not a 6. Meaning we have a 7, 8, 9 pair, triple. Wow, triple over here. Cool. Okay. Does that help, is the question. Oh, I see, hold on. I was saying that pink couldn't be on the Renban line, but neither can blue. Blue can't be on the Renban line either for the exact same reason. So in both cases, we're going to have to at the very least eliminate 8 and 9 from that set of 6. Which means that we only really have 7 digits to choose from. And because we only have 7 digits to choose from, which is 1 to 7, we must always contain the middle 5 digits 2, 3, 4, 5, and 6. Which means 2, 3, 4, 5, and 6 are always going to be on the line somewhere. That is pretty useful. But I don't like this marking at all. Okay, I'm just gonna mark 2 and 6. 2 and 6 on the outsides to sort of indicate that this contains the set from 2 to 6. Now obviously 2s can't be here because they require 2 1s to form. So 2s can't be on the outside. The 1 3 over here implies that 3 can only be one of those cells as well. Which implies that that digit cannot be a 3, because wherever 3 is here would see that digit. Oh, I see. There you go. This... Oh, no, wait, hold on. No, this could contain a 7 in it. Yeah, I was like... Those digits have to sum to at least 10, right? But for them to sum to at least 10, must they include a 6? And the answer is no, because they could be 7 and something else. They could be 7 3 or 7 5. It's like, if you only had digits 1 to 6 here, then yeah, to sum to 10, you would have a 6 here. But no, this could have a 7 in it. Oh, it can't have a 7 in it. Wait, it's even better. It must be 1 to 6. Hold on. Yeah, because look at that. That digit also plays a part. Okay, I think this is a horrible color, but I think that's the only one I have to use here. Orange? Green. Maybe let's use a green here. Sure. This digit always sees every one of those as well. So yeah, this digit, this blue digit, cannot be here. This pink digit cannot be here. And this green digit also can't be there. So wow, all of these 3 digits, because they are on the Riemann line, are different, and all 3 of those digits cannot be on this line over here. So amazingly, this just has to be the digits from 1 to 6 because they cannot contain 7, 8, and 9. And we can work from there because we can remove a lot of stuff. 1 and 3 can't be in those cells because of here. 2 can't be on the arrow. But even better, for those digits, because they must sum to at least 10, having 4 and 5 here will only sum to 9, so you must have a 6 in it. You could have 6, 5 or 6, 4 though. So it's not entirely for certain which one is the one used. But at the very least, we can remove 6 from the outside. Wow, that's awesome. That's so cool. Alright, 1 clearly cannot be there either. Because 1... Yeah, in fact, so 1 can't be here. On this line of the arrow. Interesting. Oh, hold on. 1 and 3 can't be on the 5? Wait, how is that going to be working then? Wait a minute. If 1 and 3 can't be on the 5, then how do you make 5? Because you can't use 1, 4 or 2, 3 anymore. Wait a minute. Did I do something wrong? I feel like I did something wrong. Wait. I've overstepped. Overstepped here. The 5. Is there any possible way to hit the 5 that I'm just not thinking of? Or is it really not possible at this point? Wait, yeah, it's really not possible, is it? No 3's allowed, no 1's allowed. What? Hang on. Okay, back up. Is this not really a 1, 2, 3, 4, 5, 6? Could this be a 6? How do I remove 6 from that? Because if this was a 6, then none of those digits can be 6, and then there must be a 4, 5, and 6 in here. Wait a minute. Is it true? I was like, if we ignore this, right? Let's say we ignore this and let's see how it goes, right? This is either going to contain a 1, 4 or 2, 3. Meaning it's either going to contain a 1 or a 3 in it. But here, considering that 3, because 3 has to be here, would have to be in one of those cells, that cannot have a 3 in it. Would have to be 1, 4. Which now means that 1 cannot be on the line, and therefore the line has to be 2, 3, 4, 5, 6, 7. Is that okay? I don't think so. Because 2, 3, 4, 5, 6, 7 implies that 7 can't be anywhere here. Well, 7 has to be one of those digits, right? That digit can't be a 7 as a result. But whichever 7 is, would not be on the line either. I'm generally wondering if this is an actual mistake that I've made. Have I made a certain assumption that is wrong? I could have, somewhere in my marking, made an incorrect assumption about the colors that are on the sides right now. Like maybe somehow, I think we say pink can't be here either, because you can't have 7, 8 or 9 here, otherwise you repeat a digit. There is a 1, 2 or 3. But doesn't that then mean pink has to be here? Because that digit can't be pink because it's already cyan. Which now means pink in this box has to be up here, right? And that would imply that pink can't be in here. Or here, because the pink over here would see it. And then isn't the same thing for blue, where that digit can't be blue? Because this digit cannot be at least a 7, it's at most a 6. So blue has to be here, which means it's here. Which means that now again, because of this over here, none of those digits can be blue. And in fact, that digit also cannot be anywhere on this line. And therefore this would have to be at least a 7. Which now then means this has to be 1 to 6. Because there are 6 cells, right? Yeah. And if this was 1 to 6, 1 and 3 have to be up here somewhere. But now that eliminates possibilities from 5. And that makes 5 impossible. Can this really be solved? See, I don't want to go to the solver yet to actually make sure this is solvable. But based on all my ideas so far, unless I've done something horribly wrong, which is more likely the case, this is actually not solvable to me right now. So maybe I did something wrong by, like, at the very original step, where I said that, you know, when I said that this has to be here and this has to be here, maybe there was something wrong with that kind of thinking. Or it is in fact possible for that digit to lie like somewhere here or something. I don't think so. Because again, for that to happen, this would have to be a 7. But if 7 was already on the arrow, that would have to sum to 17 at least. But with the 7 on the circle, you couldn't make those digits sum to 17 at all. So I feel like this is right. In fact, I feel like everything I've done is right, but you know, it's always gonna be something I've missed, right? Alright, I have returned and I have new insights. Unfortunately, yeah, there is a mistake that I made in this specific blue coloring over here. I said that because blue can't be here and can't be there, it must be in here. But that's where I was wrong. It's because this stupid pink thing that I made absolutely misled me. Blue can in fact be in this set, because wherever pink is, blue could just be the other one. So I thought that because I placed like pink on both of these cells, right? I just assumed both of them were pink and none of them could be blue. But that's absolutely wrong. It's could be one of each. I don't know how I'm supposed to, you know, use that information now, because I can't say that I bifurcated and say that, well, if this blue was up here, then it's not solvable. That's a horrible way to solve a puzzle. So I think I'm gonna stay here at this specific point and figure out how it's solved from here. So, whatever this digit is, we again know that whatever that digit is cannot be from here. And because this must have 4 and 6, this cannot have 6 on it. Must have anything from 4 to 6. You know, this cannot have a 6 in it. So yeah, this is still right. Because regardless of whatever we did with the blue here, this is still accurate. And I think from here, we can actually use the 5 cage now. Because if I mean, okay, if we think about it, must have a 3 in it. If it did not have a 3 in it, then it would have to be the digits 4, 5, 6, 7, 8, 9, which would always see that cell, which means that cell would have nothing left. So if 3 was not on the line, then 7, 8, and 9 would have to be on the line, which means that has no options. So 3 must be on the line somewhere, and because it can't be there, it would have to be up here. And that will give us more information, because in this 5, which now cannot be 2, 3, must be 1, 4. So yeah, this is a step I think I completely missed. We can remove 3 from that cell and 1 from that cell as a bonus. We can remove 4 from those cells as a bonus. And 4 is not in one of those cells and in one of those cells, which means that in this box, 4 has to be here. So okay, we have put 1, 2, 3, and 4 on this arrow. Amazing. Does that tell us anything? 4 can be here because of the 1, 4 pair. But I think that does tell us something. Is that 1, 2, 3, 5, 6 is no longer a solution. That doesn't really do much, does it? Because even though 1, 2, 3, 5, 6 is not a possible combination here, that adds up to 17, which is still makeable with 1, 2, 3, 4, 7. So yeah. Okay. Well, what else can we do? Well, blue we cannot actually confirm is on the line, because blue could be in here. You know, we can confirm that pink is not on the line, because the pinks here would always see those cells. So yeah, in fact, green is never on the line, and pink is never on the line. Meaning, at the very least, we have to exclude 8 and 9 from this set. So when I said we had to choose from 1 to 7, I was saying that for the wrong reason, but that is the right deduction. We can choose from 1 to 7. And so, besides 3, 4, 5, and 6 being on the line, 2 must also be on the line. So it's either 1, 2, 3, 4, 5, 6, or 2, 3, 4, 5, 6, 7. So 2 is also on the line somewhere. And, well, obviously 2 can't be in those cells. Oh, it's even better than that. Look at that. The 5 and the 4, yeah, 1 is not on the line, see? So 1 is not on the line, meaning we do have our entire set. It must be 2 to 7. There you go. 2, 3, 4, 5, 6, 7. And that helps us make this not a 7. 2 cannot be here firstly, but I guess we can do more. 4 can be here, 3 can be here. So yeah, this is 2, 3, 4, 5, 6, 7. My gosh. Does this help us? I think it does. Yes. Because we know 7 is on the line. Pink can't be 7, because we know pink is not on the line, and so if 7 is on the line, it cannot be pink. By some random equivalence logic, I think. So 7 can't be pink, meaning that in this triple of 7, 8, and 9 here, the 7 must be blue. So there you go, our first digits. And I'm so sorry that I messed this up. I hope you'll forgive me for, you know, cutting and trying to figure this out like alone before coming back to it. I did use a solver to try and figure out if there was a solution to this, but that solver has a feature where it doesn't show you the solution and just checks for uniqueness and validity. So yeah, whoa. Yeah. Alright, let's keep going though. We now know that digit has to be a 7. And because 7 is one of those cells, in this box, 7 can't be in those cells either. So in this box, 7 has to be in those 3 cells, and we already know 7 can't be there. So 7 is one of those cells over here. And because 7 is blue, and we know pink is over here, then we know those digits are blue and pink. Can I? Yes, blue and pink. There you go. Which now means that this digit has to be 7, 8, and 9 as well. In fact, both digits have to be 7, 8, and 9 because they are blue and pink. That digit, therefore, I'm pretty sure cannot be a 4. So 4 has to be here, because 4 is nowhere near 7, 8, and 9 to make this 3-length Renban work. So 4 has to be here. This digit also can't be a 2, so it must be an 8, I'm pretty sure. Yeah, because 2 is nowhere near 7, 8, or 9 either. So this must be an 8. So now that digit cannot be an 8, and we have a 7, 9 pair. That does do more for us, because we now know pink and blue are 7 and 9. So this has to be 9. And therefore that digit will be an 8. Cool, cool, cool. 7 and 9 means this sums to 16, and because we have 1, 2, 3, and 4, the 5 digits we need here are 1, 2, 3, 4, and 6 to make 16. And the last digit here would be a 5 to to finish the box. So yeah, awesome. This now forms a pair with that, which I think has to be 2 and 6. We can remove 1 and 4 from here. We can remove 3 from here. I think that's basically all we can do. Alright. Very cool. I think that was the toughest part of this puzzle. And it should hopefully open itself up now. Okay, what do I do here? I mean, if this is a 7, there must be a 1 in those cells somewhere. It could be anywhere though, fully honestly. Could be here, could be here. I guess, can we figure out what that digit is? I think it could be a 6 with a 876. It could be 789 as well. I think this has to be a 6 or a 7. If this was a 7, oh no, because we get 9 as well. This could be 879. Oh, but it can't. Alright, hold on. hold on. I think this has to be a 6, right? And this has to be a 7. Because if this is a 9, then this has to be a 7. But this also has to be a 7 because of the 9 here, which would force repeated digits. So this must be a 7. And now that must be a 9. And therefore this digit can't be a 9. But to make a set of 3 consecutive, that must be a 6. So there you go. I think that's how you resolve that. So I can color more stuff in. I'm not going to color all the digits, but yeah. Alright, we got some stuff over here. So those sum to 9, which could tell us something, maybe? I don't know. What could it tell us? I mean, this could still be 1 if those add to 8. I think that's plausible. Sorry, brain is trying to brain right now. Can we say whatever that digit is? I mean, those still sum to at least 10, which means that digit is like at least a 3, even though it can't be 3. I guess that digit is equal to the sum of those digits, which means those digits sum to at least 10. But yeah, that really wouldn't help. Nope. Alright, are we still in the tough part of this puzzle? Are we really still in the tough part of this puzzle? Wow. That's pretty insane. Oh, is it this 7? Oh yeah, I really should have looked at this cell. If this is a 7, then this only has 2 other options. It's either 1 and 6 or 2 and 5. Yeah, alright, fine. Yeah, I guess since 4 is one of those, we can move 4 from here. But I think that means that because this is 1, 2, 5, and 6. Oh, the 5 here means this can't be a 5. Wow. So that can't be 2, which means it must be 6. So 2 goes there, 1 goes there to make 7. And now this is a triple that we are working with. That makes sense. Can we do anything with that? 1 in this box must be here, which means this is a triple. Okay, we're getting there. This has to be 5, 6, and 8, which means here 5 and 6 cannot exist, which means this cannot have a 2, 4, 7 in them. So it becomes a 3, 5, 6 triple. Cool. Oh, and I realized this now can't be a 4, because if it was a 4, this would have to be a 1, 3 pair, and that would have no option anymore. So this can't be a 4, it has to be a 7. And so those digits sum to a 7. This could still be 3 though, but again, those sum to at least 10. Oh wait, that's also a triple. I didn't realize that. This has to be what? 5, 6, 3, 3, 5, 6, which means that digit can't be a 6 anymore. Yeah, definitely still thinking that there might be some tough stuff in here. The Renban lines in the corners we haven't used yet. We haven't used the arrows down here. So yeah, it's definitely possible to pack more challenge into this puzzle than right now. But okay, let's keep going. This forms a triple, I think. Yeah, it does. It has to be 289, which means that this can no longer be a 2. Oh, nice, chocolate teapot. That rarely ever happens outside of a gas puzzle. But yay, chocolate teapot. Anyway, this also forms a triple. I think they have to be 3, 4, and 5. Which helps, because of this 9 here, those digits have to sum to 8, and the only way to do that with the digits we have is 3 and 5. So that digit now cannot be a 3 or a 5, it must be a 4. Which means that's a 2, that's a 3. And I guess the 3 over here would have... No, it wouldn't. Yeah, no, it wouldn't. This is a 2-4 pair. Alright, well... I don't know what I was saying, but okay, here we are. This must be 1, 4, 9, I think. And this clearly cannot be a 1, because 2 digits cannot sum to 1. It could be a 4 though, because this could still be a 1, 3 pair. Those digits are 2, 6, and 8. That digit cannot be a 6 by Sudoku. Can we do this? Oh, we can! Wow, the 1, 2 over here means that this cannot be a 1, 6 or a 2, 5. So to make 7 you need 3 and 4. Which means that now can't be a 3. So this is at least a 5 now, because it can't be 1 or 2 either. But it can't be 6 or 7, so it has to be 5, 8, or 9. Can we make 5? I don't even think we can make 5, yeah, because 3 and 4 here eliminates 2, 3, and 1, 4 from possibility, so this can't be a 5. Cool. And so this is either 8 or 9, but... Are there any problems with that? There could be problems with that. 7? 7 has 2 options in this box. 7 could be with 2 to make 9. Yeah, okay. 5? No, I don't think we have enough digits to see anything here yet. But okay. Oh, you know what? It's probably the Redmond lines, right? Like, those lines are connected. So this might be more important, maybe. I mean, 9 could still be with 6, and 5 and 4 is in this, and 7, 8 is in the center. Right? It's like 9 is really far away from anything in here, but 9 could still be with a 6. And that's valid. Except that it's not, because of this cell, which can't be 7 or 8. So 9 here would need to be with 6, because if it was with 5 or anything lower than that, there would not be enough digits here to bridge the gap between 5 and 9. So 9 would need to be with 6, and therefore between them must be 7 and 8 to form your set of 4 consecutive digits. However, that digit cannot be 7 or 8. So whatever you put in here, because this can't be 7 or 8, you cannot put 7 and 8 in this line to form your digits. So that digit therefore cannot be a 9. And I think at this point I might as well just uncolor all of these. That's the wrong color. There you go. But this could be a 8 with a 6, I think. And you could have an... Oh, hold on. This digit is interesting. No, this could still be a 5. Like 8, 6, 5, 7 or something like this. That's valid. But this digit is actually not 6, 7, 8 or 9. So this is at most a 5. I mean, would that work? 2 could be with a lot of these. Yeah, 2 with 3 gives us a lot of options. 2 with 6 requires 3 and... oh wait, 2 can't be with 6. 2 can't be with 6 because you need 3, 4, and 5 between them. But 8 can be with 6, so that's okay. Okay. We did a lot of work just to eliminate that 1 digit. Can we do the same over here? Like, 9 could be with a lot of this stuff. 9 could be with 8 or 6. I don't think any of these digits have enough restriction as much as that digit would be. Yeah, because this could be a 7 or an 8. This could also be a 7 or an 8. So yeah, this could be a 9 with a 6. It could be a 9 with an 8. 4 could be with 5 or 6. So no, nothing much over there. Maybe it's this 4 being on this arrow? Isn't 1, 3 still valid here? Oh, it's not, because of this. Wait, hold on, yeah, that's really weird. 4 here doesn't work, because if this was 4, this must be 1, 3. But 4 here and 1, 3 here means that digit can't be 3 or 4, which breaks. So this can't be 4, it's a 9. Which is pink, but am I Too lazy to color it? No, I'll color it. So this digit now can't be a 5 because again, we don't have enough digits to bridge between 5 and 9. Alright. So that's a much better place to start. To make 9 over here, well, we can't use a 7, so it can't be 2, 7. But I think it could be a lot of other things. Yeah. Could be a lot of other things as well. Oh, this 9 means that's an 8, sorry. And so those digits sum to 8, but cannot use 6 or 3. So it can't be 2, 6 or 3, 5, it must be 1, 7, I think. So this 7 resolves that. It can't be 2 4s either, because obviously they will repeat. Those digits have to be 5, 9, and 2. Sorry, I didn't say that in order. This can't be 2. 5, 9. Don't know what that does. This can't be 8 anymore. Actually, to make 9, yeah, it can't be 2, 7 or 1, 8 now. I think it could still be 3, 6 or 4, 5 though. I haven't eliminated any of them yet. Although, okay, 9 being on a Rembrandt line is pretty useful because to make 4 consecutive digits with a 9 in them, you must use 9, 8, 7, 6. So I guess we can place 6, 7, and 8 in those digits. This can't be a 7 by Sudoku, that can't be a 6 by Sudoku. And in fact, because that forms a 6, 8 pair, because all digits here are distinct, that digit must just be a 7. Cool. Awesome, awesome. So that's more digits to go. 6, 8 over here means that digit, oh wow, interesting. That digit now can't be a 6 or an 8. Because those are two different digits, so they are both 6 and 8. Therefore, if this was 6 or 8, it would see either this or that. So this can't be 6 or 8, that's a 5. I don't think I've ever used that piece of logic before, that's a new one to me. Yeah, I don't think I've ever seen that before. I think it's just very rare for you to have pairs in diagonals, which is why that happens. Yeah, I've never seen that. That's actually kind of cool. Alright, what next? Can I do anything here? Probably, but just something I'm not seeing. Like... no. Is it this? I don't think so. Well, I mean, what could this not be? We haven't figured out what the 7 even is yet. Because it could be anything, I believe. Yeah, it could be anything. Okay. Can we see what that digit is? It's almost a 5 again. But 8, 7, 5, 6 is a valid set. Unless it isn't. No, it is valid. Yeah, I think it is. I think it's just barely valid. Like, it sets up all of these triples to work out exactly as they should. It's like 6 here, 5 here, 9 here. And then 3 here and then 5 here it works out. Alright, I shouldn't be staring at this line anymore. I don't believe it's gonna give me anything new. Whoa, I can place a 7 in this box. Oh, I didn't see that. 7 in one of those cells. 7 can't be on this arrow because it's always less than a 7. And so you can't have 7 plus something add up to something that's less than 7. 7 must go here. Which allows us to place 7 in this box. It must be there. So 7 goes there. Which means now that it can't be a 7 here. So I guess this can't be an 8. And 8 requires a 7 to pair with it along a line. Because this 8 must be, at the very best, 9, 8, 7, 6. And either that or 8, 7, 6, 5. So 8 needs a 7. But since 7 cannot be anywhere on the line, it can't be 8's. There can't be an 8 on the line either. So it must be a 2 then. And 2 can't be with 6 because there will be too many digits between them to bridge the gap, giving us 3, 5. That's a pair, meaning 6 goes here. Now 2 with 5 implies that this would be a 3, 4 pair, while 2 with 3 gives us a lot more stuff to work with here, although the 1s here imply that none of those can be 1s either. So if it was 2, 3, this would be 4, 5. If it was 2, 5, this would be 3, 4. And so in either case, this has to be 2, 3, 4, 5, right? Yeah, and another easier way to say that is because 1 cannot be on the line at all. 2 is at the quote-unquote at the very end. and therefore it will have to be 2, 3, 4, and 5 no matter what. So there you go. 3 and 4 actually gives us a 5 there, which means we can resolve all of this. That's 3, that's 4, that's 5. 5 here means 9 goes there. This forms a 2, 5 pair down there. That digit is just a free digit. That would be an 8. Sorry, can't really read very well. 9 goes here, 8 goes there. 5 now can be over here, but that doesn't really help. We have more to go. This is 2 and 3, which we can resolve. So that now can be a 3. And the last digits we have here are 1, 6, and 9. Nice. And 9 can't be there. Awesome. Alright, that was a pretty cool piece of logic to gain from that. I wonder why this puzzle is called Kodiak. From what I remember, is Kodiak? No, I was gonna say Kodiak is a camera company, but that's Kodak. That's like barely even close to Kodiak. Should I go look it up? Let me go look up what Kodiak is about. It's a city in Alaska. Oh. What does it look like? Oh, it's a bear type. It's a species of bear as well. Probably from Kodiak, the city. I mean, yeah. Does this resemble a bear? Sort of. If you look at it diagonally, this is like could be the snout, I guess. I don't know. Okay, I should not be getting distracted. What do we have? I mean, we're almost done, I think. I say that and then hopefully I don't, but I probably will spend like the next 10 minutes just staring at this again. Is it those? Can I work with this? 6 here will require 1, 5 because 2, 4 is not available. 5 will require 1, 4, which doesn't work. There you go. 5 here cannot be 1, 4 because this would have no option, but it can't be 2, 3 either because they're already in the row. So this can't be a 5, it has to be a 6, which means that has to be a 1, 5 because 2 is not allowed, so it can't be 2, 4. So this is 1, 5, which resolves this 1, 4 pair over here. 1, 5 also removes 1 from that cell, and so actually 6 resolves this entirely. That's a 9. 1 resolves this 1, 6 pair, the other way around. And this now has to be a 3, so 5 goes down there. That's a free 8. And because those sum to 7, they cannot be 1, 6 or 2, 5. They have to be 3 and 4. That resolves this. This 3 resolves the 1, 3 down here, which does something. Those last 3 digits are 2, 6, and 9. 9 here come in those cells, so 9 goes there. This forms a 2, 6 pair, which probably resolves somewhere, but I don't see it. No, 8 goes here, which resolves this, so that's a 6. That's an 8. 6 means that must be an 8, which means in this triple here, 8 must be up there. Cool. Those last 3 digits would have to be 2, 5, and 9. And 9 come in those cells, so 9 has to be here. 2, 5 forms another pair over there, which is okay. That does form a pair over here, in fact, so that can't be 5 anymore, that's 3. 5 goes here, which resolves everything over here. 2 means this is resolved. What else is resolved? I don't see what. Those digits form a triple, which have to consist of 3, 4, and 8. No, 3, 4, and 6. And the only way to make 9 with those digits are 3 and 6. So this must be 4, that must be 3. 3, 6, yeah, we can resolve. And this 6 helps us resolve a bunch of stuff. 2, 6 is resolved, 2, 4 is resolved. 5 here resolves this 1, 5, which we could have done earlier, but we didn't. This is a 1, 4 pair, which we can resolve with this, and we're almost done. That final 1, 4 pair is resolvable. Nice, solving the puzzle in 57 minutes and 2 seconds. Wow, this was a trip. A real trip, actually. Oh, but we're done. Oh, I really like the first few ideas in this puzzle. Even though I really missed something that was very important, I assumed something extra about this puzzle that I should not have assumed. But yeah, in fact, just the break-in itself was very cool to go through. Felt like a sort of math kind of thing. But yeah, alright, well I hope you enjoyed this video as well. I'll see you guys next time. Bye bye.